As promised in the previous chapter, we will complete our proof that the norm of x minus y is a distance function. All that was left to prove was the triangle inequality. For all x, y and z in Rn, dxz is less than or equal to dxy plus dyz. So in our case, the norm of x minus z is less than or equal to the norm of x minus y plus the norm of y minus z. We could prove this directly, but instead, we are going to prove that the norm of a plus b is less than or equal to the norm of a plus the norm of b for all a, b in Rn. The result then follows by substituting a equals x minus y and b equals y minus z. The reason for this detour is threefold. First, this form of triangle inequality is less cumbersome as it involves two variables as opposed to three. Secondly, this form has a geometric meaning that you are already familiar with. Namely, the length of one side of a triangle is smaller than the sum of the length of the other two sides. But most importantly, besides Cauchy-Schwarz, this form of triangle inequality will be your most useful tool in this course. Theorem: triangle inequality. For any a and b in Rn, the norm of a plus b is less than or equal to the norm of a plus the norm of b. To prove this, we will expand the norm of a plus b squared using dot product properties. From this expanded expression, we form an inequality by applying Cauchy-Schwarz on the dot product term. Then we complete the proof by rooting both sides of this inequality. Proof: we once again square the norm and exploit dot product properties. The norm of a plus b squared is the same as the dot product of a plus b with itself. Expanding or foiling this expression, we get a dot a plus 2a dot b plus b dot b. Converting dot products back to norms, this is the norm of a squared plus the norm of b squared plus 2a dot b. Of course, any number is less than or equal to its absolute value, so in particular, a dot b is less than or equal to the absolute value of a dot b. Thus, the norm of a squared plus the norm of b squared plus 2a dot b is bounded up by the norm of a squared plus the norm of b squared plus 2 absolute value a dot b. By Cauchy-Schwarz, the absolute value of a dot b is less than or equal to the norm of a times norm of b. Hence, we can bound the right-hand side further by the norm of a squared plus the norm of b squared plus 2 norm a norm b. Comparing our initial expression with the final upper bound, we have the norm of a plus b squared is less than or equal to the norm of a squared plus norm of b squared plus 2 norm a norm b. But the right-hand side is the same as norm of a plus norm of b squared. We then finish the proof by rooting both sides.